In the past two lessons, we talked about conformational isomers of the same molecule, which we visualized with Newman projections. We then talked about conformational isomers of rings, with particular attention to cyclohexane and its chair conformations. We also noticed that in rings, we could have stereoisomers because the ring constrains groups from switching between cis and trans isomers. In this lesson, we'll talk about constitutional isomers, and in the following chapter, we'll have many more examples of stereoisomers, including enantiomers. Constitutional isomers are some of the easiest to differentiate because they have different physical connections, rather than just differences in space. Remember, though, that all isomers, no matter what type, must have the same formula. Otherwise, they're just two molecules. I hope the big bold letters here really gave you most of the picture. If molecules have the same formula but have a different connectivity, they are constitutional isomers. This could include a change in functional group, like cyclobutane and 1-butene, or it could just be a different bonding pattern, like a methyl cyclopropane instead of a cyclobutane, or a 2-butene or a 2-methylpropene instead of a 1-butene. Sometimes molecules look like they could be different molecules because they are drawn in different configurations. The IUPAC rules for nomenclature allow for you to arrive at the same name with different configurations. If you can name a molecule correctly, you can usually catch if molecules are really just configurational isomers. Pause and try naming these two molecules as a review. Both molecules are 2,4 dimethylhexanes and are therefore configurational isomers, not constitutional isomers. Since hydrogens are rarely shown in a molecule, it is sometimes difficult to gauge whether structures have the same number of hydrogens or not, or whether they can even be isomers of each other. To talk about the number of hydrogens on an organic molecule, we talk about saturation. Saturated hydrocarbons have single bonds and no rings. We use these as a reference for all molecules with the same number of carbons, since they will be at a maximum ratio of hydrogens to carbon. Each degree of unsaturation, which also goes by the name of index of hydrogen deficiency, or IHD, corresponds to 2 hydrogens fewer than the saturated molecule of the same number of carbons. To calculate the IHD, first take the number of hydrogens in a saturated molecule, which always ends up being twice the number of carbons plus 2 extra for the hydrogens that are at the end carbons. Then subtract the actual number of hydrogens that are on the molecule you're interested in and divide by 2. So for example, butene has 8 hydrogens, while butane, the saturated version, has 10. We take 10 minus 8 and divide that by 2, indicating a degree of unsaturation, or 1 index of hydrogen deficiency. This is a pain to calculate in a lot of cases because things besides carbon and hydrogen often have a special accounting system. We'll go over these later, but many times it's easier to look for groups that change the index of hydrogen deficiency whenever they appear. Rings are a great example of this since they take away the end carbons that would normally have extra hydrogens and always add 1 index of hydrogen deficiency per ring. Double bonds, since atoms need one of their bonds to be to each other instead of to hydrogen, also result in 1 more index of hydrogen deficiency every time they appear. Triple bonds add 2 indices of hydrogen deficiency. You could also think about this as each ring and pi bond adding 1 index of hydrogen deficiency, if that's easier for you to see. With this shortcut, we can quickly look at a set of molecules and see if they might have the same formula. For example, cyclobutane and 1-butene have the same number of carbons, and we can see that since one has a ring and the other has a double bond, they each have 1 index of hydrogen deficiency and therefore the same number of hydrogens. The idea of saturation is used widely. For example, you might obsessively look at nutrition labels and notice that some fats, which we really mean fatty acids in this context, are saturated, indicating that the carbons are all singly bound. Unsaturated fatty acids might be monounsaturated, which would correspond to an index of hydrogen deficiency of 1, or poly, which would indicate an index of hydrogen deficiency of greater than 1. Trans fat is also called out in nutrition labeling since naturally occurring unsaturation is generally cis. However, trans fat less than 0.5 grams doesn't need to be labeled. So in nutrition labels, 0 grams of trans fat doesn't mean the same thing as no trans fat. What a world. While we are on the topic of saturated fatty acids, it's useful to note that saturated fatty acids generally have more conformations available to them, including the all-anti conformation. This creates a lot of contact between molecules, and melting points for these fatty acids tend to be very high, high enough that they tend to be solid. However, each cis double bond creates a location that must be kinked, and the molecules become harder to stack. So every time you have unsaturation, it's harder to stack the molecules. London forces plummet then between molecules, and the unsaturated fatty acids tend to have lower melting points to the point of generally being liquid at room temperature. Plant fatty acids tend to have more unsaturation and therefore be liquid. We often talk about plant fatty acid derivatives as vegetable oils. Animal fatty acids tend to be more saturated and therefore more solid, so we talk about animal fats. There are of course exceptions like mostly saturated coconut and palm oils that are solid-ish at room temperature, or cold water fish that are rich in unsaturated fats. This is an area where the physical properties and 3D geometries play a huge role in food science, and there's a lot more to explore here that we're not going to get into. We can calculate index of hydrogen deficiency from a molecular formula. As we have indicated before, a straight chain alkane will always have the formula CnH2n plus 2, or for every carbon, there are 2 hydrogens plus 2 extra. Anytime there are 2 hydrogens missing from that, we have an index of hydrogen deficiency. So we subtract out our actual formula and divide by 2. However, we need to account for other atoms as well. Halogens substitute for hydrogens 1 for 1, so we just count halogens as if they were hydrogens. Because chalcogens, like oxygen, have 2 bonds, they can be inserted between atoms without affecting the carbon to hydrogen ratio. So we just ignore chalcogens, so oxygen and sulfur ignored. Pnictogens, that's the nitrogen group, tend to add to hydrogens along with 2 bonds. So we should have an extra hydrogen every time there is a nitrogen that's been added. The easiest way to account for this is to count nitrogens as a negative hydrogen. Drawing all the constitutional isomers for a formula can be a challenge, but it's a helpful way of developing an eye for the relationships between molecules. There are multiple ways to approach this type of problem, but the first step should always be an index of hydrogen deficiency to determine if rings and double bonds can be included. A next step could be to draw all possible connectivities without worrying about multiple bonds or substituents. When I do this, I usually will start with a straight chain of atoms and then move carbons from the end to every other position one by one. Then I take every branch chain that I created and repeat. Because rings are connected differently than other unsaturated molecules, these should be included here, with care not to exceed the index of hydrogen deficiency. After a list of possible skeletal structures is created, take each one and add double or triple bonds to every possible location that will give the correct index of hydrogen deficiency. After this list is created, add substituents to all possible locations. At the end of this process, you should end up with all possible constitutional isomers. Try to follow these steps to draw all constitutional isomers with the formula C6H14. I drew 1 to get you started, but there are 4 more. Pause and don't continue until you find at least 3 of them. These 5 molecules are the 5 constitutional isomers, all that have the formula C6H14. There are 8 of these isomers that I expect you to get, although one that you might list is actually 2 separate isomers. Pause and try to get at least 7 with this formula before continuing and checking your work. These are the 8 isomers, but this isomer actually has 2 enantiomers, the type of isomers that we're going to talk about in the next chapter. For now, I'll just show you that the two versions of this molecule have different orientations in space at the 3 position. So you can have the hydrogen pointed forward or pointed back. If you weren't already convinced that understanding structural relationships between molecules was important, let me leave you with a parting example. D-glucose, perhaps the most important carbohydrate biologically, exists as dry as a straight chain, but isomerizes into 2 constitutional isomers, an alpha and a beta form. When glucose goes through glycolysis to be converted into pyruvate and eventually energy, some of the initial steps involve adding a phosphate and then isomerizing the glucose phosphate to a fructose phosphate. And besides these specific examples, every 6-carbon carbohydrate is actually an isomer, constitutional or otherwise, of glucose and fructose.